Okay, starts walking at 0, -2 in the direction of 5, 1. That's that vector there. Ends up at point 2, 3. And then the question is, at what point did he make the turn? So first we got to conceive the question correctly, and a picture is super important, right? Draw pictures. This is a heavily geometry course. That means when you're solving problems, you're drawing pictures of the situation. Okay? So, question is, where does he make the turn? Okay, so we need to think about what tools we have to do this. So maybe one hint to get us started would be, could we make the vector from 0, -2 to 2, 3? Start. Would that help? So create that vector. And now, by looking at the situation, that blue vector, really what would solve this problem? What would solve this problem is if we had this red vector right here. See that? If we knew that, then we'd be home free, right? We'd have this. If we had this vector, then we'd have the starting point 0, -2, and we could easily get the coordinates of that point there. So make the blue vector. Do we have a tool to? So this is not for you to answer, but to think about if you still haven't gotten this problem yet. Do we have a tool that helps us get this red vector? If so, we're home free because you got the starting point, you got the vector, which is basically the changes, starting point, changes, final points. So I'll just give you that. That's your hint. Does that help? Those who haven't gotten it yet? Okay. All right, what's the next one here? So then if it's not coming to you, then you need to review Wednesday's class. This Wednesday's class, I gave you a really good tool to help with this problem. Next, I think number 10. Okay, so they're asking for, is that a bit bigger? Does not. Oh, that doesn't work. I can't use my pen. So just redraw the picture. So here you have the distance. You want the distance of P through the line through points. I think you have kind of two questions like this, right? They're basically, in this one they give you a picture. So I got A and B. And I've got those coordinates. And then point P, say, it might be here, it might be over here. It doesn't matter where it is, just for the sake of the picture. I'll just draw it somewhere. And then we're looking for what, this distance right here. Okay, so make some vectors, see if they help. So what could we do? We could kind of like the same thing as before. We could make this the vector from A to P. We can make the vector from A to B. I think having this point right here is really similar to the Gandalf the Gray problem. So having that point right there, I think, could kind of seal the deal for finding the distance from that point to point P. So I think if you uncrack the Gandalf problem, I think you can also, this is really similar. So right vector AB, right vector AP, and then think about how could if I could get the coordinates of this point, I could easily find that distance. Okay, if you need more help, you can use the email instructor button. So you can always use this. Just give me a nice detailed explanation of where you're at in the problem, what your progress. It's down here at the bottom. You see that underneath the screen? So that's at the bottom. So you can use that. Just give me a detailed explanation of where you're at, what your progress is, and then also if you send a separate email with like a picture of your work, that's great too. Okay. If you don't think the written explanation is enough, then go ahead and send me an explanation. This is what I've done so far. This is, but I'm still not getting it right. Okay, and I'm happy to dialogue with you over email about these. I also have office hours today, 1 to 2:30 after class. Okay, so let's press on. Any questions? So you guys did the cross product worksheet, did you? So these first 7 kind of tell the story or give you a good idea of what the story is. So what happens? We start off with 2 parallel vectors. And what did the cross product end up being? Yeah, this is called the 0 vector. It has 0 magnitude, so the components are all 0. It has 0 magnitude, and has really no direction. Right? If it has no magnitude, then it doesn't have any direction at all. So that's what we call the 0 vector. All right, and so then also here you have the 2 vectors are both that, and you get the 0 vector. So if the 2 vectors are, what can we say about these 2 situations? What are these called? The vectors are parallel, right? So same direction or exactly the opposite direction. Parallel vectors, you get 0 vector, okay? Then what happens? So basically all these examples take this first vector here, call it vector A, and take it, if you notice, just sweep it around, kind of like the unit circle, right? What quadrant is this here? What quadrant is this right here? This is the x-axis and the y-axis. This is quadrant 1. Is that right? And then this over here is quadrant 2. So I'm basically taking this first vector, if you noticed, and sweeping it around the unit circle, starting at angle 0, and then acute angles, and then somewhere over here is this one. This is 90 degrees, right? And what do we get for that? What's the magnitude of this first vector? 3, 0, 3, 0 would be 3. Magnitude of this vector? The magnitude. 3, right? 3. Magnitude is always positive, it's like the length. And what do we get for the magnitude of the final? 9. So where is that 9 coming from? This is to feel similar to what we've seen before with dot product. The 9 is coming from. Is that a hand, Chris? Oh. 3 times 3, right? The product of the magnitudes, right? But now, when do you get the product of the magnitudes with cross product? When the vectors are orthogonal. What was it with dot product? Opposite or parallel, right? So you got like the maximum or the maximum negative in dot product when they were parallel. And what happened when they were 0 for dot product? 0, right? 0. Dot product was 0 when they were when they were perpendicular. But now with cross product, what happens? We got parallel vectors gives a dot product or cross product of 0, and then orthogonal gives max product of the magnitudes. So it's like the inverse situation in terms of the magnitude of the cross product, right? Which is if you're just talking about the magnitude of this vector that's the cross product, it's like the inverse situation of the dot product. So we could say the magnitude of the cross product is, how could we make a definition like we did for the dot product? Magnitude of the cross product is, we say for dot product. I know Nick knows. Anybody else? So let's go back to dot product. What was the meaning of the dot product? The dot product is, that value is? Anybody? Who said it? Someone sort of say it.
The product of the vectors magnitudes, but only as much as they're the same.
Right. Do you remember this? You need to remember it. And in this course, it's especially important that you're retaining what we've done before. When we get to the last month of the course, it's using everything we've done prior. Okay, so dot product was only, maybe it was the long weekend, okay, or something, but, well, it's actually 2 days ago, right? So the dot product is the product of the magnitudes, but Only as much as they're in the same direction. Product of the magnitudes as much as they're in the same direction. So now, how could you make a similar kind of definition or meaning for cross product? It's the product of the magnitudes. I'm just going to write it out this way. The product of the magnitudes, but only as much as in the same direction. And what mathematical thing is that? As much of one as is in the direction of the other. Cosine. Okay? The product of the magnitudes, but only as much as they're in the same direction. Cross product. Now we're seeing the magnitude of the cross product, because it's a vector, not a scalar, is product of the magnitudes as much as they are orthogonal, perpendicular to each other. When they're perpendicular, you get the product of the magnitudes. When they're parallel, they're not orthogonal at all, and you get 0. Is this making sense? Now that's just the magnitude of the cross product. So what we saw was, as this first angle swung around, what happened to the cross product? It got bigger and bigger until max was at when the vectors were 90 degrees orthogonal. And then as you continue to swing, come in and make it smaller and smaller, it gets smaller and smaller until 0 again. Okay, but the cross product is a vector. It's not a. So this is the magnitude of the cross product is only half of the deal. The other half is the direction. What's the direction of the cross product? Because it's a vector, right? It's a vector. So let's take a look at this one here. So this was our say A cross B. So to get the they're actually. What did you notice about the cross product? You should have noticed that it's always orthogonal to the original two vectors. Do you notice that all these vectors were in the xy plane, all these starting vectors? And then the resulting cross product was always orthogonal to the xy plane, right? So if you have two vectors in the xy plane, then the resulting cross product is orthogonal to that, or in the z direction, k direction. But there's two possibilities, right? Not only up, it could also be down. So that's where the right-hand rule comes in. The right-hand rule tells you, so in terms of the direction of the cross product, first of all, it's orthogonal to the plane of the two original vectors. But then you have to figure out which direction, because there's two orthogonal directions. So what you do, the right-hand rule, have we done the right-hand rule yet or something else? You did. So the right-hand rule, so if you have your right hand and you extend your index finger like toward the window, and then your third finger would be towards you guys and thumb up. So then you put your index finger in the direction of the first vector. You orient your hand so that your index finger is in the direction of the first vector, and your third finger is in the direction of the second vector, and then your thumb will tell you the direction of the cross product. Okay, so I gotta get my hand so that my index finger points in the direction of A, and my third finger points in the direction of B, and then my thumb points up. So I think I've got it right now. See that? Index finger is the positive Y. My third finger is negative X. So my thumb is now telling me that it should point up and not down. Does that make sense? And that's kind of true for all of these first 7. Okay. Okay, so that kind of puts it all together, right? So we know the magnitude of the cross product is the product of the magnitudes as much as those vectors are orthogonal. And that's the relationship of sign. And then the direction is going to be orthogonal to the plane or to the two starting vectors, and then according to the right-hand rule. Okay, so let's look at an example down below. So let's look at that's the one I want. the last one. So let's sketch those two vectors. 0, negative 2, 0 would be this. And then 4, 0, 1. 4, 0, 1 would be like this. Okay, what can you say about those two vectors? Anything you can say about the spatial relationship of those two vectors? Are they orthogonal? Yeah, aren't they? Any vector, so since this vector is on the y-axis, wouldn't any vector parallel to the xz plane be orthogonal to it? Do you see that? I could take this vector and spin it around on the xz plane, and all those vectors would be orthogonal to this one. Agree? Do you see that? Therefore, what do we expect for the magnitude of the cross product of this? What's that? Max, and how do we get that max? Product of the magnitudes, right? So I've got orthogonal vectors. So this one has magnitude 2. This one has magnitude what? Square root of 17. So the resulting cross product has magnitude what? 2 square root of 17. And then what about the direction? So there's two possible directions. Either, do you see it's like, it's kind of, the direction that's orthogonal to both of those is kind of like the z-axis, but maybe tilted a little bit. Do you see that? So maybe like, either like this or like this. Do you see that that line is the perpendicular line to those two? So like if my z-axis is like this, the orthogonal possibilities would be like if I tipped it back a little bit like this. Agree? So now, according to the right-hand rule, which is it? Up, mostly up, a little bit back, or mostly down and a little bit front? So I need to what? I'm doing negative 2, 0, so I gotta put my index finger in that direction. So then my third finger points in this direction. So it's the one that's going to be up and back. It's my thumb. See that? So this is what we're expecting for the cross product. It would be magnitude 2 radical 17 in this direction here, up and a little bit back. So I'm going to show you how to actually get the components of the cross product. And then once we get the components, we'll compare to what we just concluded about the magnitude and the direction, and see that that makes sense. So here's how you finding the cross product. You're going to make a 3 by 3 vector, or 3 by 3 matrix. 3 by 3 matrix. The first row of the matrix will be I, j, k vectors. Second row of the matrix will be the components of the first vector. Was that the 0, negative 2, 0? Is that the first vector? Did anybody write it down? Is that right? Thank you. And then the second vector was the 4, 0, 1. So we make a 3 by 3 vector out of those. And the cross product, it turns out, is the determinant of that 3 by 3. So if you've had some linear algebra and you've done determinants before, any way you could find the determinant of that will work. I'm going to show you my preferred way, but if you've done it before and you have a different way of finding the determinant, you're welcome to use it. So we want to find the determinant of that matrix. Here's the way that I would suggest that you do it. Repeat the first two rows over here. So repeat columns, I, 0, 4, first column. And then repeat the second column, j, negative 2, 0. And then now there's 3 diagonals down to the right of 3 values. So those 3 diagonals are, bringing out all the colors today. So here's the first, starting at I got a first diagonal down to the right, starting at the j, second diagonal, starting with the k, I got 3 diagonals down to the right. What I'm going to do is I'm going to multiply down each of those diagonals and add those up. So I'm going to, first product is negative 2i. See that? And then 0j. And then 0k. Okay, and then I'm going to do the same thing again, but with diagonals that go down to the left. So let's see, how about orange? So down to the left, starting with the k, going down this way, and then I going down this way, and then j going down this way. And after you do this a few times, you'll be able to do this without writing down those columns. You can just do it with the original 9 things by kind of wrapping around. But we'll start off by writing them out. So and now when I go down to the left, I'm going to multiply and I'm going to subtract those. Okay, so I'm going to multiply and subtract. So this is going to be what, minus negative 8k. Is that right? Then minus 0i. And then minus 0j. Do you follow it? Did others do? So down to the right, you're going to multiply and add. Down to the left, multiply and subtract. And then we just combine them all, and that should be the cross product, and it should agree with what we came up with before. So what's our I component? It's like negative 2i, and then plus 8k. Okay, or same exact thing is negative 2, what? Negative 2, 8? 0, 8. So let's start with the magnitude first. Magnitude equals square root of 4 plus 64, 68. Which is 4, is that 4 times 17? So therefore, I'm getting low there. I'm going to still get some room. Is that what we said the magnitude was? Product of the magnitudes of the original vectors, because they started out, they were orthogonal to start. Okay? And then what about the direction? Remember what our direction was? It was what we said, like in the xz plane. So here's xz plane, and then tip back a little bit, right? Is that what we got? Negative 2, 0, 8. Does that agree with that? Yeah, a little bit back, negative 2, and a lot up, 8, and in the xz plane. So that checks out. So then, if you want, like I said, if you want to write out the, if you want to write these first 2 columns out again and do it explicitly this way, that's perfectly fine. But after you've done that a few times, you can do it without doing that. All right, and so you just have to wrap around, right? So, like, you'd have positive 5i, and then what, 12j, do you see that? 12j, and then 3k. So 5i plus 12j, k coming down this way, so plus 3k. Do you see that? Without having to write down those 2 columns again. And then minus, this way, negative 2k, minus 18i, minus negative 5j. But if you need to write out, so if you don't sure where I came up with those numbers, write the first 2 columns again and do what I did over here, and then you'll see it. But eventually, it's helpful just to be able to do it without writing out the first 2 columns. Questions on computing the cross product algebraically to get the components? Does it make sense? But then what you get should agree with this concept of it, right? That the magnitude of the cross product, one more time, is product of the magnitudes of the vectors, but only as much as they're orthogonal, or that's where the sine theta comes in. All right? And the direction is, this is super important. You've got two vectors. The direction of the cross product is orthogonal to both, orthogonal to the plane of those two vectors. And then which way? There's two choices. Right-hand rule will seal the deal. Okay, so let's look at some applications of cross product. Any questions? So let's just quickly. No. Scalar multiplication multiplies a what by a what and results in a what? Vector by scalar and gives you a vector, right? So you're scaling one vector by some scaling factor, right? You're shrinking it or stretching it, but then you also might flip it if that scalar is negative, right? Dot product multiplies what by what and gives you a what? Vector by vector gives you a scalar. And we've talked about the meaning many times. Cross product multiplies a vector by vector gives another vector. We just covered the meaning of that. All right, so here's the deal. Dot product versus in applications. So the dot product, what? That's for quantities that are optimized or maximized when the contributing vectors are in the same direction or zero and orthogonal. So what's an example of that? What's an example of when your quantity is optimized or maximized when the two vectors are in the same direction, but there's zero when they're orthogonal? Yeah. Oh, cool. Yeah, that's cool. Yeah, like the direction of he said solar panel. Oh, is that what you want? Is it optimized when they're in the same direction? So yeah.
Well, yes. Because if it's parallel to the sun, then it would be optimized. But if it's like perpendicular to the sun, then it would be you would get any energy.
I think maybe you're thinking the right thing, but you're using the words parallel and perpendicular incorrectly. Right? You want, for the optimization, you want the sun's rays to be what? Yeah. I think you're thinking the right thing. You just mixed up your terms. Okay, so what's an example of this? Yeah. Work, right? Force and displacement. We get the optimum work when your force is in the same direction as displacement. That's why work was dot product. Get that? Okay, so so cross product is for quantities that are optimized or maximized when the contributing vectors are orthogonal. So this would be like a solar panel example. Okay? And zero when parallel, right? So first, how about torque? Dot or cross product. So what is torque? Torque is amount of twisting force. So this is a force vector right here. And this is called the radial vector. So it's a vector from the center of rotation to where you're applying the force. Okay, so R is the vector, it's like stands for radius. It's like from the center of rotation, the bolt in this case, to where you're applying the force. Okay, and so what do we think? Is torque going to be dot product or cross product? Is torque going to be dot product or cross product? Nick knows. So torque is twisting force. Is that going to be maximized when these are orthogonal or parallel? He wants orthogonal. Agree with that? Yeah, what happens if they're parallel? Then what happens to the bolt? Nothing, right? So the parallel component of this force does nothing to twist the bolt. The orthogonal portion of the force does everything to twist the bolt. Do you see that? Okay, so what is the twisting force? So to see what angle we need here, if I place F back here, this is the angle theta here. So this is our key component. Is that right there? Is that sine theta? So is this theta right here? Theta is always the angle when the vectors are tail to tail. That's why I took the force and moved it back so you could see what theta was. I just took the force and replayed it, positioned it, so you could see what the angle theta is. So in this triangle, where is theta? Is it exhibit A or exhibit B? B. That's theta. Right? The angle between the vectors when they're tail to tail. So then this, sine theta or cosine theta? Sine, opposite side, right? See, it's opposite side. And that makes sense that's cross product because we got using sine. So this is magnitude of F sine theta. So the torque, the magnitude of the torque is going to be the length of the moment arm times the part of the force that's actually turning this thing, which is, so this is force times the lever arm. And it turns out, that torque is a vector, right? So torque is a vector. So if it's a vector, how would we find the vector? If this is the magnitude of it, what vector has this magnitude? What vector has the magnitude, the product of the magnitudes, in as much as they're in orthogonal direction? Cross product, right? That's the magnitude, that's the magnitude of the cross product. That means torque has a direction. It's a vector. So what direction is torque relative to the screen and the bolt? What direction is the torque? Right-hand rule. So what do you think?
It's
Coming towards you out of the screen. Do you agree? Point your, we're doing R first. Point your index finger in the direction of R so that your third finger is in the direction of F. And your thumb tells you what direction the torque is. So the torque is actually orthogonal to the screen, right? The torque is this way. It's orthogonal to the plane of rotation. Again, index finger in the direction of the pink radial vector, third finger in the direction of force. That means that torque is coming out. All right? And what happens when you, so this is really cool, what happens when you turn a wrench in that direction? What happens to the bolt? That's counterclockwise, right? Which way does the bolt go? Towards you. The direction of the cross product. Isn't that cool? When you twist a wrench like this, rotate like this, the bolt comes out of the screen. That's the direction of the torque. The vector is this way. And its magnitude is how much twisting force, right? How much twisting force you're applying. Righty-tighty, lefty-loosey. Right? Make sense? Okay, so that's torque. Another example. So torque is cross product. So how about the next one? Area. So here I'm showing two vectors, and I'm laying the second one, or maybe that's the first one. Anyway, one of those vectors rotate like that. And do you see that given any two vectors tail to tail, that creates a unique parallelogram? Do you see that? So any two vectors tail to tail creates a unique parallelogram. So the area of that parallelogram, would that be a matter of dot product or cross product? The area of that parallelogram. Dot product or cross product? Remember, dot product is when you get a maximum situation when they're in the same direction. Cross product, maximum situation when they're orthogonal. So area is a matter of cross product. Cross product. So let's just pause this somewhere here and figure that out. Figure out what is the area of a, so I'll call this vector A, and vector B, and this is the angle between them. So before we talk to anything about vectors, how do you find the area of a parallelogram? Area of a parallelogram is? Do you know how to, what is it? Magnitude of A times magnitude of B, is that right? For a parallelogram? You're on the right track. That would be if it was a rectangle, but I got a parallelogram now. So what do I have to adjust?
Like if you made a line from like perpendicular to the tip.
Right, and what do we call that? That's right. What is that for the parallelogram? That's the height, right? So the area of the parallelogram is? Base times height. How can we express the base here? Not B. Magnitude of B, right? B is a vector. So the base times the height. Go ahead, Andrew.
I was going to say magnitude of A times the sine of theta.
Right, and to get the height, you would do, he's saying magnitude of A sine theta. Do you see that? That's the opposite side. So the base, magnitude of the base times the height, which is magnitude of A sine theta. And what is that? Magnitude of cross product. Right? It's not the cross product, it's the magnitude of it. Because the cross product is a vector. So which way would this the cross product point in this case? Where would the cross product point? So it's either going to be out of the board screen or into the screen. So so you get your right hand, you position your hand so that your index finger points in the direction of the first vector, and your third finger points in the direction of the second vector. So it's like that, and so that would be into the screen. So A cross B, in this case, it points into the screen, orthogonal. And the magnitude of A cross B turns out to be the area of the parallelogram that's formed, the unique parallelogram that's formed by those two vectors when you put them tail to tail, say. So this is going to be a really important concept at the end of the course. This A cross B is called an area vector. Its magnitude is the area of the unique parallelogram formed by A and B, and its direction is orthogonal to the plane of that parallelogram. We're going to see that in the end. It's called an area vector. Okay, so yeah, please, Becca.
Just a little bit off topic from the area.
Yeah, sure.
But couldn't you just use the dot product to find, like from like the web work, to find that distance t that's perpendicular to if the cross product is that height? You know?
So this one, so the dot product could get us, let's see. I think the dot product could help us get this vector here. Is that what you're seeing? What's that?
I meant cross product for that.
Okay.
So if cross product is the height,
Yeah.
we could use that on the web work to find that distance from like point P.
It's related to the height, right? So the magnitude. So yes, yeah, okay, exactly. So this right here is the height. So then the magnitude of the cross product divided by the magnitude of B. Is that what you're saying? Take the magnitude of the cross product and divide by the magnitude of B. That would get you that height. Is that what you're saying?
Kind of. Not, yeah, kind of.
Right? Because that's you're saying this is the height.
Yeah.
So if you want to use cross product to get that height, then you're saying it's the magnitude of the cross product divided by the magnitude of B.
So you would have to know the magnitude of the cross product.
You could take the cross product, you get the components, take the cross product like the way I showed you earlier, find its magnitude, divide by the magnitude of B, and that would be that height right there. It might be a little more work than using dot product, but it would work.
So we can't use the dot product to find
To find what?
the height.
And how would you use the dot product to find the height?
So what do you do, like A minus the rejection of A on B?
Good. Yeah, because, right. These two vectors together form A. So the projection of A onto B would be this vector. So this vector would be the A vector minus the projection. And it would be this vector. Yep, good. Totally. Other questions, comments, discussion? Yes, please.
When you're picking the first vector,
Yeah.
do you always pick the one with the smaller magnitude?
No. Doesn't matter.
It doesn't matter.
Nope. So if you did B cross A, you'd get the exact same magnitude, the area of the parallelogram, but they would just be in the opposite direction now. So you're doing B cross A, you would have B this way, and then A this way, and now your B cross A would be coming out at you. That would be the only difference of B cross A from A cross B. Magnitudes are the same, opposite direction. Does that make sense?
Wait, you could use either dot or cross product. Wait, never mind.
Yeah, sure. Yeah, so the cross product is more directly related to this opposite side of the angle, right? Because it's like sine of theta. And the dot product is more directly related to this adjacent side, this component. But you can use either to find either, just maybe one's a longer way around.
How do you determine which one would be A, like your first one? You just go with
Whatever you name
A.
it, whatever you call it, right? So however you label the vectors, you just have to be consistent then. Yeah. Yes?
Is the cross product commutative, or
So magnitude, yes, but direction, no. That's what I was saying. Like, so if you do A cross B, then you have A cross B directions into the board. But if you do B cross A, then you have B cross A comes out. The magnitude is commutative, but your direction will be opposite if you change the order. Yeah. Okay, one more little thing to look at here. Okay, this thing. This is called, I don't know if I'll spell it right, a parallelepiped, or is there no e's? It's just parallelepiped. Do you know parallelepiped?
I think it's just parallel.
So it's a prism, basically. Okay, so I made a parallelogram A and B, and then you have in the third dimension you have some C that makes this like three-dimensional parallelogram. Okay, so if this, and I want to find the volume of that. This is angle theta. So using vectors, so what is the volume of this? Don't look it up. Try to figure it out. This is fun to figure out. Don't look it up. It ruins it, right? So volume in terms of, as a function of A, B, and C. What formula using vectors A, B, and C will find the volume of this thing? So I'll give you one hint. The volume is area of the base times height. Area of the base, because it's a rectangular prism, area of the base times height. So how can you get the area of the base of this thing times the height using vectors A, B, and C? This is a fun little puzzle. I'll take attendance. See, area of the base we should know already. What's that? Magnitude of the cross product. So the area of the base, magnitude of A cross B. Now we want to multiply that by the height. So what's the height? The height is this right here, right? What direction is A cross B? Isn't it up?
Yeah.
So the vector A cross B has this direction of this axis right here. You see that? So look what I want. I want to multiply the magnitude of A cross B, what, times the magnitude of C, but as much as in this direction, right? Don't I want the magnitude of C that's as much as it is in the direction of A cross B? And what's that? Dot product, right? I want the magnitude of C, but only as much of it as is in the direction of this vector. Therefore, the whole volume is A cross B dot C. It's both. It's cross product to get the area of the base, but then we can use that vector, which is in the direction of the height, and take as much of the magnitude of C in that direction. That gives us the height of it. Did anyone get it before I started?
I thought it was that, but then I was like, that's too easy.
Did you get it?
You had it.
Yeah, but it's cool, isn't it? I mean, so we can use not only the magnitude of this parallelogram, but the direction of it. We want to be how much of C we want in that direction. That's dot product. So that's the volume.